Ground is a term used to indicate connecting a component to the vehicle frame or chassis. Current flows from the positive terminal of the battery through a controlling device such as a switch, then through the component. The return path is through the vehicle chassis or frame to complete the circuit and allow the component to operate. Using the vehicle frame in this way simplifies the circuit wiring. A tachometer is used to indicate engine RPM. It is normally connected to the negative terminal of the ignition coil. The pulses from the ignition primary circuit are then used as an input to operate the tachometer. At idle speed, the frequency of the pulse is steady. As the engine speed rises, the frequency of the pulse increases as the tachometer indicates. A tachometric relay uses the same input from the negative side of the ignition coil to ensure the relay operates only when the engine speed is above a specified minimum, say 350 RPM. In this case, it operates as a safety device, ensuring the fuel pump operates only when the engine speed exceeds this figure. The term stoichiometric ratio describes the chemically correct air-fuel ratio necessary to achieve complete combustion of the fuel. It is represented by the Greek letter lambda. The value of the ratio is 14.7 parts of air to 1 part of fuel. By mass, that's 14.7 kilograms of air to each kilogram of fuel. So if lambda equals 1, the air-fuel mixture is at the stoichiometric ratio of 14.7 to 1. If an air-fuel mixture has a higher figure, say 1.03, there is more air in proportion to the fuel than 14.7 to 1, and the mixture is slightly lean. A mixture with a lower lambda value has less air, proportionately, than fuel, and the mixture is slightly rich. The exhaust gas oxygen sensor is also called the lambda sensor, since it can be used to maintain the air-fuel ratio at lambda equal to 1, within very close limits. It can be installed in the exhaust manifold, where it measures the percentage of oxygen in the exhaust gases. A high percentage of oxygen may mean too little fuel is entering the engine, the mixture is too lean, and the lambda is greater than 1. The sensor delivers this information to the ECU, which adjusts the mixture accordingly. Similarly, a low percentage of oxygen may indicate too much fuel is entering the engine, the mixture is too rich, and the lambda is less than 1. A potentiometer is a mechanically variable resistor which, in EFI applications, is normally a film type. It can be linear or circular in construction and has 3 electrical connecting points. 2 are at the ends of the resistor and the third is attached to a center sliding contact, arranged to move across the resistor. A reference voltage is applied to the resistor so that a steady current flows through it. As the center sliding contact moves across the resistor, it measures the voltage at the point it is in contact with, and provides a reference voltage for that position. In automotive applications, the circular form is commonly used as a throttle position sensor, with the center contact attached to the throttle plate. The throttle plate position can then be monitored by the control unit. The density of air is its mass per unit volume. This means a volume of air at high density has a higher mass than the same volume at low density. And if there is a larger mass of air, it will contain proportionally more oxygen. The density of air in the atmosphere changes at different temperatures and altitudes. That means the air that enters an engine at different locations could have very different amounts of oxygen. The amount of oxygen in air directly affects how well it supports combustion, so it can be important in determining an air-fuel ratio for an engine. Pressure and vacuum are terms in everyday use in the automotive industry. Manufacturers recommend a pressure to which tyres need to be inflated, and manifold vacuum is used to operate a brake booster. Gases exert pressure on all bodies they make contact with. This applies also to the air in Earth's atmosphere. Air has mass, and as a result it exerts pressure, called atmospheric pressure, not only on the Earth's surface, but also on all objects on the Earth's surface. Atmospheric pressure varies with altitude, but at sea level it is calculated as 101.3 kilonewtons per square metre, or 101.3 kilopascals. But if this is so, why does a pressure gauge read 0 when it is not in use? This is because the gauge indicates pressure above atmospheric pressure only. This reading is called gauge pressure. If absolute pressure was needed, an absolute pressure gauge would be needed, and it would read 101.3 kilopascals when not in use. Absolute pressure equals gauge pressure plus atmospheric pressure. Readings on an oil pressure gauge or on a tyre gauge should really have 101.3 kilopascals added to them. It is normal practice, however, for the gauge reading alone to be taken as the accepted value. If pressure being measured is below atmospheric, a pressure gauge with its 0 reading is of no value. This is why, for pressures below atmospheric, as in a manifold vacuum or depression, a vacuum gauge is normally used. In a petrol engine, the position of the throttle plate controls the volume of air, or air-fuel mixture, entering the manifold. At idle speed, the pistons draw air away from the manifold at a faster rate than it can pass the throttle plate into the manifold. A high vacuum, or a depression, exists. At wide open throttle, depending on load, the vacuum is much less, and pressure in the manifold rises, closer to atmospheric. A vacuum gauge can be calibrated in millimeters of mercury, and the scale reads from 0 to 760. The scale is derived from the fact that atmospheric pressure supports a column of mercury 760 millimeters high. This glass tube, closed at one end, is filled with mercury, then inverted in a bowl of mercury. The column of mercury in the tube falls to about 760 millimeters. The space above the mercury is a vacuum, and the atmospheric pressure on the exposed surface of the mercury supports the column. At sea level, atmospheric pressure supports a column of mercury 760 millimeters. But at higher altitude, its height falls, which indicates that atmospheric pressure at that altitude is less. A scale of 0 to 760 millimeters can thus be used to indicate the degree of vacuum or depression that exists below atmospheric pressure. At idle speeds, a vacuum gauge connected to the intake manifold will indicate a reading of approximately 450 to 500 millimeters of mercury, depending on altitude. Some engine management systems signal changes in atmospheric pressure by using a barometric pressure sensor in the ECU. This is because, above sea level, air pressure is reduced. So to maintain correct air-fuel ratio, a vehicle has to reduce the amount of fuel delivered to the engine. Volumetric efficiency compares the volume of air entering a cylinder during intake to the internal volume of the cylinder when the piston is at bottom dead center. It is usually expressed as a percentage. In a naturally aspirated engine, one without forced induction, volumetric efficiency can never be 100%. This is because of the resistance to the airflow that occurs at the carburetor, manifold, and the intake valve. With forced induction, the incoming air is compressed so that a greater volume and mass of air is forced into the cylinder during the intake stroke. That takes the volumetric efficiency to above 100%.
This section examines basic principles of electronic fuel injection. Because of the need to comply with exhaust emission regulations, the modern petrol engine requires a fuel system of extreme accuracy and long-term reliability. A correctly matched air-fuel ratio must be available at all times and under all conditions. This is satisfactorily achieved by electronic fuel injection. EFI is a pressurized indirect injection system that uses solenoid-operated injectors with a fixed orifice. When they're energized, fuel passes through the injector body. This arrangement is called a multi-point system. One injector is located in each intake manifold runner or pipe adjacent to each cylinder. An electronic control unit, or ECU, opens the injectors by pulsing their electrical current. They spray fuel into each intake port directly in front of each intake valve. Fuel leaving the nozzle is atomized, and it mixes with the air also entering the system to form a combustible mixture. Fuel pressure is kept at a constant value above manifold pressure, so that the amount of fuel injected is determined only by the length of time the injector is held open by the ECU. This is called the pulse width of the injector. The triggering signal to operate the injectors can be supplied from the ignition system or from crank angle sensors on the crankshaft or the camshaft. Engine fuel requirements change according to engine speed, load, and temperature, so the ECU needs information on these changes. Sensors measure these variables, then relay the information to the ECU in the form of electrical signals. The ECU then calculates the duration of pulses necessary to provide the fuel required. Extra fuel required during cold starting can be supplied by increasing the number of injection pulses, or by fitting a separate cold start injector that operates independently of the main injectors when the engine is cranking. The throttle body injection system, also called a central fuel injection system, has a single injector, or in some cases 2 injectors, mounted in a carburetor-like throttle body. The throttle body assembly is fitted to the flange of the intake manifold, and the fuel is sprayed into the intake air entering the manifold. The air-fuel mixture is then carried through the manifold into the engine. Fuel pressure is maintained at a constant value, and an ECU pulses the injector or injectors. This section examines petrol fuel. Petroleum or crude oil is taken out of the ground as a mix of impurities and highly flammable compounds of hydrogen and carbon, called hydrocarbons. It is processed into many products, including petrol and diesel fuel. Petrol is used in different forms in different engines. It is very volatile, mixing easily with air to form gas or vapour. The more effectively liquid petrol is changed into vapour, the more efficiently it burns in the engine, so high volatility is desirable. How petrol burns must be controlled. If it burns too quickly, it can cause detonation, sometimes called ping or knock. So special additives are used to slow down the rate of combustion. Octane rating is a measure of how well a petrol resists detonation. The higher the rating, the less likely it is that detonation will occur. Higher operating pressures in the combustion chamber can also cause abnormal combustion. A lead-based anti-knock additive used in leaded petrol can allow these higher pressures without loss of performance. Lead additives are also lubricants. In high-compression engines, lead compounds coat valve faces and seats and help prevent wear. Leaded petrol is used in older cars that have few or no emission controls. It should never be used in engines designed for unleaded fuel. Governments now limit levels of lead in petrol, and unleaded petrol is replacing leaded petrol. So-called unleaded petrol may contain small amounts of lead, but maximum levels are tightly controlled. For petrol to burn properly, it must be mixed with the right amount of air. For a petrol engine, the air-fuel ratio by mass is about 15 to 1. By volume, it's about 11,000 to 1. Not much petrol, but lots of air. A lean air-fuel mixture has more air in proportion to the amount of fuel. A slightly lean mixture gives good fuel economy and low exhaust emissions, suitable for cruising conditions. A mixture that's too lean can make an engine run roughly and overheat. A rich air-fuel mixture has less air in proportion to the amount of fuel. A slightly rich mixture can produce more power at lower temperatures, but the extra fuel it uses steps up fuel consumption and emissions. A too rich mixture fouls spark plugs and causes incomplete burning, and that reduces power. In normal combustion, the spark plug ignites the mixture and a small ball of flame forms around the tip of the plug. The piston compresses the mixture, the flame spreads faster and moves evenly to halfway through the mixture. The piston reaches top dead center. The flame picks up more speed, then shoots out to consume the rest of the mixture. Combustion ends with the piston a short way down the cylinder. Detonation is a violent collision of flame fronts in the cylinder caused by uncontrolled combustion. It occurs after the spark plug has fired. The sudden rise in pressure can cause a knocking sound. Sustained detonations can lift temperatures enough to cause pre-ignition, also called auto-ignition. Pre-ignition occurs before normal combustion, when something in the combustion chamber heats up enough to ignite the mixture before the spark plug fires. A mixture may also ignite simply because it is unstable under the higher heat and pressure. Detonation and pre-ignition can cause severe damage and must be avoided. Engine management systems use knock sensors to detect detonation, and they retard ignition to stop it. This section examines the air supply. In multi-point injection systems, the air required for the combustion of the fuel is led from the air filter through the throttle valve and into the common manifold or plenum chamber. From here, individual intake runners or pipes branch off to each cylinder. All of these pipes are of equal length. The design of the intake system determines how large an air mass can be drawn into a cylinder at any given engine RPM. This is where most advantage can be taken of electronic fuel injection, since it can achieve exactly uniform distribution of the air delivered to the cylinders. With unobstructed passages to each cylinder, the cylinder fills with air as efficiently as possible. The breathing of the engine, or its volumetric efficiency, is improved. The more air crammed into the cylinder, the denser the air-fuel mixture when ignition occurs. This increases the thrust on the piston and increases engine power output too. The temperature of the air influences how dense the air-fuel mixture will be. Cold air is denser than hot air, so it has a greater mass in any given volume. This is why, on most intake systems, the air entry to the intake is away from engine heat, to ensure the entry of cool air. Since the manifold carries air only, it doesn't need to be heated by coolant. Filtered air arrives at the intake port as cold and dense as possible, ready for mixing with the fuel from the injector. The amount of air entering the engine must be measured, so that the amount of fuel injected into it forms a mixture to suit the engine operating conditions at that time. The volume of air entering the engine varies according to the position of the accelerator pedal and the engine speed and load. Changes in volume are reflected in changes in manifold pressure between the throttle plate and the intake ports. When the pistons draw air away from the manifold more quickly than air can pass the throttle plate into it, the pressure in the manifold falls. At idle speeds, this pressure is low. A high depression or a vacuum exists. As the throttle plate opens, the pressure approaches that of the atmosphere. The depression or vacuum tends to fall in value. Devices measuring air entering the engine send a varying electrical signal to the ECU. The signal can be a measure of the volume of air or of the manifold pressure. In both cases, this information is combined with the engine speed signal to provide the basic setting for the injector pulse width. An airflow meter measures the volume of filtered air entering the engine. It can be mounted on the air filter casing or close by. All air entering the intake flows through the meter, then through a sealed flexible hose or duct to the throttle body, then enters the engine. Vane-type airflow meters have a spring-loaded vane or flap, which deflects according to how much air enters. The electrical signal to the ECU varies with this deflection, as contacts attached to the vane move across a potentiometer. The intake system must be airtight, with no leaks downstream of the meter, otherwise inaccurate signals will be sent to the ECU. Manifold pressure sensors measure pressure in the manifold. One common type has a small connect. This section examines the fuel supply system. The purpose of any fuel supply system is to deliver fuel to the engine in a form in which it can mix with air to form a combustible mixture. The fuel must be finely atomized to mix with the air. This is why injection systems deliver the fuel under pressure. The EFI system is a circulation system. Fuel is drawn from the tank by a fuel pump and delivered to solenoid-operated injection valves. Fuel pressure at the valves is maintained by a fuel pressure regulator, and excess fuel flows back to the tank through a return line. The fuel filter is directional. It is fitted between the pump and injection valves to stop contaminants reaching other parts of the system. The fuel pump can be mounted externally on the chassis frame or submerged in the fuel in the tank. It is electrically operated and electronically controlled. It is driven by a permanent magnet electric motor, a sealed unit integral with the pump. Fuel flows through the pump and around the electric motor when it is running. There is never an ignitable mixture inside the pump housing, so there is no danger of explosion. The pump delivers more fuel than the maximum requirement of the engine, so pressure in the fuel circulation system is maintained at all times. A fuel pressure regulator maintains fuel pressure between the pump and the injectors. In multi-point injection systems, the fuel pressure regulator has an inlet connection from the fuel rail and an outlet that lets fuel return to the tank. A control diaphragm and pressure spring determines the exposed opening of the outlet and the amount of fuel that can return. So the strength of the pressure spring determines fuel pressure in the fuel rail and keeps it at a fixed value. However, the pressure in the intake manifold varies considerably with changes in engine speed and with load, so the pressure drop across the injector must also be taken into account. For any injection duration, if fuel is held at constant pressure, then as manifold pressure varies, so does the amount of fuel delivered. That means fuel pressure must be held constant above manifold pressure. This is done by sealing the spring housing of the pressure regulator and letting it sense manifold pressure via a connecting hose. Then, when the manifold pressure alters, so does the fuel pressure. When manifold pressure is low, as at idling, fuel pressure is low. As manifold pressure rises towards open throttle, so does fuel pressure. Since the injectors are all subjected to the same pressure, they all inject an equal amount of fuel. The quantity of fuel delivered is thus controlled very accurately by the pulse width of the injector. Manifold pressure sensing is not required in throttle body systems, as the injection occurs above the throttle plate at atmospheric pressure. So fuel pressure is determined by the force of the regulator spring acting on the diaphragm. The injectors are sealed into the manifold by O-rings that prevent air entering at that point. The O-rings, together with plastic caps on the injector nozzles, also act as a barrier to heat being transferred to the injector body. For a short time after an engine is switched off, engine temperature keeps rising, and that can cause excessive vapour in the fuel lines. This pump stops this with a non-return valve on its outlet, which maintains the pressure in the fuel line during that short time. This pressure will decay over about 20 to 30 minutes, but it ensures effective hot starting characteristics. When the engine is running, the circulation of fuel ensures cool fuel is being delivered at all times, and vapour formation is prevented. The pump control circuit normally allows the pump to operate for a few seconds only when the ignition is switched on, and thereafter during cranking, and when the engine is running above a specified minimum RPM. This section examines electrical functions in EFI. In the electrical system, detecting elements sense engine operating conditions and relay this information in the form of electrical signals to the Electronic Control Unit, or ECU. The ECU is a small computer programmed with the operating characteristics of each individual application. This information is stored in its memory. The control unit processes input signals to determine the amount of fuel required by the engine at that instant. It then grounds the injection valve circuit to open the solenoid-operated injection valves. The length of time injectors stay open in milliseconds determines how much fuel is injected. A basic EFI system needs input signals on ignition switch operation, engine cranking, the amount of air entering the engine coolant temperature, throttle position and engine speed, and battery voltage. The varying data received from all of these inputs allows the ECU to arrive at its injection setting. This vehicle began from a cold start and has been running only a short time. It is now operating in top gear with a light throttle only. What influences its fuel requirements? A relatively small volume of air is entering the engine. The throttle position is associated with economy or cruising conditions. Engine speed is in the low to mid-range. Coolant temperature is still below normal. These factors combined produce a fuel setting. It is less than if the throttle were opened suddenly for acceleration or to overcome increased load. However, it is more than it would be if coolant temperature were at its normal level. The varying signals can be supplied by variable resistors, by switch contacts, by voltage pulses from the ignition system, or by sensors. An airflow meter varies its signal by the deflection of a vane as air enters the engine. Deflecting the vane moves contacts across a potentiometer to signal its position and thus the amount of air entering the system. The temperature sensor uses material with a negative temperature coefficient of resistance. Its resistance is high when it's cold, but it falls as its temperature rises. It's called a thermistor. This is the opposite of a normal resistor, which increases its resistance as temperature rises. The coolant temperature sensor is immersed in coolant in the cylinder head. The air temperature sensor is in the air intake at the airflow meter or in the manifold. Throttle position can be signaled by a potentiometer attached to the throttle shaft. It provides a continuous varying signal through the entire range of throttle position. Throttle position can also be signaled by a contact type switch, but it signals the idle and fully open positions only. Engine speed can be detected by a connection from the ignition system primary circuit or by a pulse generator type sensor on the crankshaft. The pulses are computed by the control unit into an engine RPM figure. They can also be used to trigger the injectors. In multi-point injection, the injectors can all be triggered at the same time. This is called simultaneous injection, and the injectors operate twice per cycle. That's once each crankshaft revolution, each time delivering half the fuel for the cycle. In a 6-cylinder engine, the injectors are triggered on every third ignition pulse. In throttle body systems, the central injector is normally triggered on every ignition pulse. However, if there are 2 injectors, alternate triggering may be used. At idling speeds, the frequency may be less to provide finer control. The actual operating time of the injectors depends very much on battery voltage. The response time to lift the injector needle to the fully open position is about 1 millisecond. If battery voltage is low, this response time takes longer and the engine receives less fuel. The ECU can compensate for this delay in opening time by extending the duration of the injection pulse. In more sophisticated engine management systems, the control unit can control additional functions such as ignition timing, injection modes, idle speed, cooling fans, and fuel pump operation. To do this, however, more inputs are needed. To control ignition timing, some systems replace the distributor with a direct fire ignition system. Between one ignition point and the next, the ECU calculates when the ignition point will occur. It then triggers the ignition accordingly. Ignition can be varied according to load, speed, coolant temperature, cranking speed, and battery voltage. Identifying number 1 cylinder and the camshaft position allows different injection modes to be used. Sequential injection means injection occurs in the sequence of the firing order. Each injector opens once only in each cycle to deliver the fuel needed. Added load placed on the engine during idle can be compensated for by increasing the passageway of an idle speed control device. This lets more air bypass the throttle plate. This air has been measured by the airflow meter, so extra fuel is metered to maintain the same air-fuel ratio. The extra mixture thus delivered increases engine torque and maintains idle speed. For efficient operation of the catalytic converter, the mixture ratio must be maintained close to the stoichiometric ratio, 14.7 parts of air to 1 part of fuel. Efficiency of combustion can be monitored by measuring the percentage of oxygen in the exhaust gas. A high percentage may mean the mixture entering the cylinder is too lean. The oxygen sensor in the exhaust manifold or in the engine pipe tells the ECU how much oxygen is in the exhaust gas. The ECU then varies injector opening time to achieve a correct mixture ratio. Feedback also lets fuel settings change as components age. This is called adaptive learning. The ECU memorizes its fuel settings for different operating conditions and stores them for future use. If a fault occurs in a component or part of a system, a fault code can be displayed on the check engine lamp in front of the driver. Alternatively, a scanning tool can be connected to a diagnostic terminal and information on the fault can be analyzed. Although most injectors operate at the nominal battery voltage of 12 volts, many sensors have a reference voltage of 5 volts. This is done by a voltage regulator in the control unit. It gives more accurate signaling, as fluctuations due to changes in battery voltage do not occur. This is a simplified wiring diagram for an EFI application. The battery is grounded to the vehicle frame at the negative terminal. Its positive terminal is connected to a tachometric relay and to the ignition switch. A connecting wire runs from the tachometric relay to the positive terminal on the fuel pump. A fuse in the connecting wire protects the circuit. The fuel pump circuit is completed by grounding the fuel pump negative terminal to the frame of the vehicle. When the fuel pump operates, current flows from the battery to the pump. It flows through the pump to rotate the armature and completes the circuit by flowing from the negative terminal through the vehicle frame to the battery negative terminal. Similarly for the other components in this simplified system. Positive connections are made to a number of components from the tachometric relay. The relay only operates when the engine is cranking or running, so no current flows in any connecting wires at other times. Identification of the sensors and their inputs allows easier identification of the wiring diagram for any given system. Follow the circuit for each component from the battery positive terminal and trace its path back to the negative terminal. Components are earthed either through the vehicle frame or the ECU. The other EFI discs in this series examine in more detail some more sophisticated engine management systems and the operation of their components. You should view these other discs. Then investigate these more complex systems for yourself.